Hello everyone and welcome back to another video of the Hidden Quantum Champions. Today we are talking about C12, the company that is using carbon nanotubes to build quantum processors based on spin qubits. And if you have heard about spin qubits before and you want to know what makes carbon spin qubits different, or if you want to learn about this basically crazy idea of using carbon nanotubes to build spin qubits, then you're exactly right here. But also if you're interested in the company itself, if you've never heard, for example, about C12 and you want to learn what this company is about, then you're exactly right here. We are talking about the company, the technology they are using, the people behind it, and what trajectory the company is on. And with that, let's get started right into it. So here we are on the website of C12. It says quantum hardware reimagined. We don't just build quantum hardware and so on and so forth. It's moving very quicker than I can read. But what we can see is already in the background, we see this golden chandelier that we know from solid state kind of quantum technology, so that we know from spin qubits, that we know from superconducting qubits. So likely we are talking about something that goes on a chip, which means it's scalable. And likely we are talking something that needs to sit at a very low temperature in this cryostat. So not something that you can drive in your living room, of course. But I mean, this is something that we know from other technologies, that we know from silicon spin qubits, that we know from superconducting qubits. Let's try to understand where it differentiates. So here it says the Paris project. And by the way, the company is based in Paris. So that is already some indication here. We are on a mission to drive one of the biggest technological breakthroughs of the century and change the course of history. So big mission ahead. And here you see the C12 machine. So looks super fancy with these golden lights and then the cryostat sitting here in the center and the controller electronics rack and so on. Then in a monumental change in computing. And I mean, here we see the typical use cases that quantum computing companies are talking about nowadays, right? Quantum chemistry, or basically material science, chemistry, everything where quantum mechanics plays an important role in creating those new materials and creating those new chemical processes, also pharmaceutical, right? Then aerospace and defense, energy and finance being mentioned here. And then some words here about the quantum artisans. I'm not going to go into the details of this. And the news section down here with the latest one, I think, being probably this one from June 4th. C12 unveils pick and place a nano assembly process to scale carbon nanotube quantum chip manufacturing. And I will talk about what I think about this in a second. But just before that, I want to say I'm recording this in July of 2026. So latest news here from June. So I would say reasonably up to date. Now, a couple of words about nanotubes and maybe also why I can actually talk a little bit about this. So I worked in a research center, the research center in Jülich, which is, I think, Germany's biggest research center. We had a super big cleanroom facility, and some of my very close colleagues were working in the field of nanowires. So there are different ways of creating these nano tube or wire objects. In this case, they were using other material systems, but the principle and the idea is similar. You have a chip or a surface, a substrate, and you are growing these kind of nanowires on top. So in the case of my colleagues back then, they would look into things like indium arsenide or some types of semiconductor, narrow gap semiconductor, core shell nanowires. I will not talk about the details. Here we are talking about pure carbon. So there is nothing else than carbon in there, C12 hence. And these are not, let's say, little wires, but they're actually tubes, so they are hollow. Think about graphene. You might have heard about graphene because there was a Nobel Prize awarded to it. It is this truly two-dimensional mesh of carbon atoms that are sitting in this honeycomb kind of structure. And if you take this sheet and you wrap it into something, then you end up with a tube. And that's what you see here on this left image, right? You see these honeycomb structures. Every single dot here is basically a carbon atom, and they're sitting in this honeycomb structure that is wrapped around into a tube. So it's basically a two-dimensional object that has this curvature that it becomes a tube. Now, what quantum physics is doing is basically in carbon, you have free moving electrons. So these tubes, they can behave like a conductor, or they can behave like an insulator. So that depends a little bit on how actually this wrapping is looking like. So quantum physics, and that's similar to the particle in a box problem, basically tells you that there are certain numbers of circumferences of these tubes where they have specific properties. And I will not be able to explain why this is the case for some and not for others. This is something about quantum mechanics. If you want to learn more about it, let me know down in the comments below. I can do a video where I try to explain this to you in a, let's say, easy way. And if you want to understand it in the details, then I'm sorry, you will have to go to study physics for that. But long story short, you can grow these using ovens, using very sophisticated growth equipment, and then you can really create those objects that are looking like little tubes under the microscope that are having this truly two-dimensional mesh, which is only carbon, no other atom sitting in there. And now you can pick and place them. So because you somehow need to get them from the growth substrate onto your silicon wafer, where you can then connect them with metallic gates, where you can drive currents and stuff like that. And there are different ways of doing that. And I need to tell it because it's kind of funny. In the old days, there was the so-called Q-tip method. So you would take a Q-tip, the one that you should not put in your ear, right? Something like this. And you would basically wipe it across the wafer where you grew all the nano objects. And then you would take it and put it on a different substrate, like just touch the substrate, and some of those nanotubes, they would stick to the Q-tip and then later on stick to the wafer. You would look with a microscope at it and then basically draw a design that connects some selected ones of those wires. Of course, this is kind of a random process. You have to redo it every single time. So that leads to this whole idea of being able to selectively grow those objects. So that's, for example, something that the let's say nanowire community has been doing and investing quite a lot of work in. Some very good friends of mine were working in the clean room to basically get this engineering challenge or this physics challenge solved of creating nanowires in very specific positions. And then you can use a microscope, a so-called scanning electron microscope that is using electrons basically to see these very tiny objects. You can use that, and you have some so-called manipulators, nano manipulators in there. So these are very, very tiny metal sticks, and you can basically touch the tube with it, and then the tube sticks to the little metal stick, and then you can place it somewhere. So you can really pick and place individual items and put them on specific locations on your chip. And that makes it very interesting because now you can be super selective, and you can basically put them in an architecture that you would like to. And this is what they are likely doing here. So they have this pick and place machine in the nano assembly. And by the way, this is super interesting. If you're looking at the company, and later on we might have some time to look at the company history, they are also very focused on the technology that builds these chips. So beyond, or let's say just besides all of the cool stuff that they are doing in the quantum computing challenge, right, of building this quantum chip, they're creating all these crazy tools that can be used to manipulate, for example, these nano objects, which is also likely interesting for other kinds of applications, right? So this is just to say, even though the main focus is, of course, on the quantum chips, they're doing a lot of crazy stuff on the way there. This is similar to when the people were trying to reach the moon, right? And suddenly a lot of new technology had to be developed that would later on lead to whole industries being developed from this. Here we have this new machinery that is being built in the clean room and being used to do this nano manipulation that can likely also be used for other kinds of processing in the future. And then, yeah, here we just see they are based in Paris in France. And I mean, that is something that we've mentioned already. Let's quickly talk about the technology. Let's see what we can see here. And I will also talk a little bit about how I understand it. I think this part here is the interesting one. So this is how they envision the system to look like. So you have your nanotube here that is being suspended like a bridge between those two elements. These are the metallic electrodes that you can basically use to insert current, to insert electrons into your nanotube. And the nanotube is basically suspended in the vacuum. What does this? Well, that creates a very, very clean atmosphere, because within the nanotube you only have carbon atoms. So that means you don't have any magnetic momentum of any like random atom that is sitting somehow close, like some impurity or something, because these tubes, these nanotubes, they are purely made out of carbon. And you don't have anything around it. It's suspended in the air, right? There's only vacuum around it when it later on sits in the system. So that makes it a very clean environment. The qubits will likely have a very high coherence time because of that, because there's not much that is kind of shaking on them and creating some kind of disturbance or moving them away from their ideal state. These are sitting on silicon wafers, so you can use standard wafer processing that is very scalable and can be used at large scale. And then you see here these little blocks down here. These are electronic gates, as far as I understand, that can be used to now separate individual individual electrons, free electrons in those nanotubes, and then, for example, move them from the left to the right, shuttle them back and forth. As far as I understand, there's another type of electrode here, that's mentioned here, magnetic gate electron, that can then also be used probably to attach to the spin property, which is the magnetic momentum that an electron has. And that's how you basically change all the modalities of your qubit, and that's how you can manipulate it. As far as I understand, the spin qubit is then addressed via microwave pulses to the control electrodes. As far as I understand, the way that then multiple of those are coupled is with a superconductive coupling element, with a superconductive resonator, for example, that basically connects multiple of these tubes and can then couple different qubits with each other so that you can also create entanglement. There's also this FAQ. I looked at it before I recorded this video. If you want to learn more about the technology and the ideas behind this, highly encouraged to read that. There are also some funny statements in here that I personally enjoyed reading this quite a lot. Besides that, there are also some publications mentioned here, and of course they also have a roadmap, as a proper quantum computing company nowadays has to have. They also have a roadmap here, and that starts with this 2027, so next year, first chip that they are announcing here, which is a 16 physical qubit chip that can then also run some error correction on top, so that you end up with one logical qubit, so that is these 16 running with error correction on top of themselves. Then you basically have some other numbers here, like logical error rate, watts per physical qubit. That is very important, right? These physical qubits, of course, they don't run on 1500 watts. So the 1500 watts are not applied to these 16 qubits themselves. They are operated usually at much, much lower powers. However, you need to cool down the cryostat, right? And that requires usually a lot of power. So your compressor that sits in the cryostat is usually already in the kilowatt range. And that's why for these 16 qubits, you have per qubit 1500 watts. So you're like in the 20k watts range, roughly 20 kilowatts range, to operate this whole system here with all the measurement electronics and cryogenics in there. But of course, as you're scaling the number of qubits on the chip, your amount of power per qubit goes down. Then there's some more information down here about the different kind of qubits, like what are the different artifacts and ideas about those, and how the layout looks like. I will not go into the details of all of this for now, but rather I want to quickly go here on the lab tour, because I also found this kind of nice. So here you see the typical chandelier. So with the different cryostat levels, you see some radio frequency lines going down here, because as we learned before, right, we are using electromagnetic waves to manipulate our spin qubits, similar to what we know from silicon spin qubits. And of course, this is happening, for example, via radio frequency signals. And usually down here at the tip of that, that's where your chip is sitting, in a little confined space that looks or is right about the size of a Coca-Cola can. So at C12, the future of computing is built by hand, one atom at a time. Behind every breakthrough lies a space designed for absolute precision, our lab in the heart of Paris. And I don't know if you know this building. If you have ever visited Paris, you should. It's a Pantheon, definitely worth a visit. And their office is actually quite close to that. So I don't know if you can zoom in here. No. So there is apparently the office, and then there is another one quite close to that. So that is anyways a very nice area within Paris. And then here there's some further tour, right? So there's the theory side, and that's what I said before, right? It is not just material scientists that are building crazy stuff on chips, but it really starts with the whole theory. So you have the theoreticians here. You have, of course, the whole material science and nanofabrication side of things that happens in clean rooms. They have expanded, I think, their clean room facilities over the years even, so they have quite a lot of expertise in that. Then, of course, you need the growth side of things that generates the nanotubes that then later on in the clean room are processed into chips. So this is this one here, so the CNT, carbon nanotube, growth team is basically creating them. Here you see one of these growth chambers that are typically used with ultra high vacuum to then grow these. There's a characterization, of course, because you want to be able to pick only specific ones of those wires and use them for your setup. Then you have this pick and place, right, with the machine that we just saw from the press release. And of course, and I mean, that is maybe not mentioned here, but of course you also have a cryogenics team, measurement electronics team that are basically setting up your quantum computer, and a software team that is then basically helping you to orchestrate. Here it is. So that's called qubit control here. And then on top you have, of course, the software that controls all of this and does the manipulation and the cloud access and so on. So you see it's a quite big team. This is not just two people that are sitting in a garage by now, but you really have people with various different backgrounds doing various different jobs within this team. And that already leads us to the about part, right? So let me quickly open that for you as well. How does the company present itself, right? So the future quantum standard, we exist to pioneer a unique approach to quantum computing that creates a utility scale quantum computer. And here is a quick overview over the time. So starting with the foundation in 2020, the Spark C12 is founded by twin brothers, Mathieu and Pierre, spinning out of the ENS physics lab in Paris with scientific advisors. And then from day one, our focus is clear: carbon, purity, and the pursuit of fault-tolerant quantum computing. Here you see the two founders. As mentioned in the description, be careful, they are twins. They look equal, but they are two different people. And then you have here the first foundation with this $10 million seed funding round and the small team at the start laying the groundwork. Then you have here the quantum fab, and that's what I was saying, right? There's a lot of nanofabrication, cryostats, and so on involved. So this is this 800 square meter fabrication hub in the middle of Paris, close to the Pantheon, I think. Then you have here, backing the ambition, a Series A round of 18 million euros. And then some publication. In the meantime, it's 50 people in 2025. And then there's this additional expenditure of 600 square meters for the next step. And then here you can basically see, let's say, the management level or the management of the whole company and the operations. You see there are a lot of people working actively in there. A couple of numbers, so 80 plus employees in the meantime. Total money raised is 25 million euros. I'm pretty sure there's going to be more to be raised in the future. And by the way, if you are interested in this whole space, or if you are, for example, thinking about investing into companies, then we might have something for you. Go check out the link down below the video, because we are starting a course that is targeting investors, people that are doing mergers and acquisitions or acquisitions in the space of quantum to put a foot into the quantum space, and also founders that are interested in understanding the quantum landscape. So we are basically expanding the idea of the hidden quantum champions into a course that will have much more compressed knowledge than watching all the 120 videos of me talking about this, but also with much different structured formats. So we will have different ways of accessing that knowledge, getting you up to speed as fast as possible, and giving you all the inside knowledge that you need to have to do your first informed steps into the quantum world. So if that's interesting to you, go check out the link below. There's some way to get more information in the video description. Now back to the video. So you see 24 nationalities, 20 plus PhDs, 11 scientific publication, patents, and so on and so forth. Gender equality index mentioned here as well. And then the partners, and a couple of those we've seen before. There is private investors, there is institutional investors. So you see, for example, here the European Innovation Council, but also Verve Ventures. You see there's public funding in there, for example, regional funding from France, academic and research partners, as well as industrial partners, for example, Quantum Machines as one of the instrument manufacturers. So you see Bull here Blue Force as the provider of the cryostats, and so on and so forth. But I think that's it. That's everything I wanted to talk about today. Of course, there's also the solutions tab here, but I don't want to jump into all of the details of this. If you found it interesting, then please give it a like and share it with a friend. I would love to see more people joining this community of quantum enthusiasts. I'm looking forward to see you again in the next video. Until then, as always, stay hydrated and bye-bye.